what effects it will cause and how we can avoid them and things like that. So precursors are something that happens prior to an event. Like in this case, we want to see if we can see any precursor that happens before a solar flare or something that happens before a coronal mass ejection happens, and to see what we can do to avoid them. So this should work. Okay, this works. So this is my overview slide. I'll talk about why prediction is necessary, what can we do to mitigate the effects, and then how I'm trying to do the mitigation, or try to get to know when it happens and how we can avoid it and things like that. So, and then I'll go into the methods of all these are my methods, and then I'll close with the timeline. So let's start with some definitions of flares, CMEs, such things, which can have effect on the our ground and then space things in space. So flares are these strong bursts of radiation that comes from the sun. This is the movie of a flare on the right hand side, and then coronal mass ejections are big blobs of plasma that gets ejected from the sun. And the solar energetic particles are basically these particles that get accelerated, like protons basically. They get accelerated during the process of reconnection during a solar flare, or in the shock front of a coronal mass ejection. And then solar wind can also cause some effects, but they are usually minimal, and they are not as strong as flares or CMEs. So this is the big picture. It shows the connectivity between the sun and the earth. We have the sun spewing plasma with the coronal mass ejection, and then the earth with the magnetosphere, the bow shock, and all of these satellites looking at the sun, either taking images or doing in situ observations of the plasma that is coming from the sun. Okay, so why are there so many satellites dedicated to looking at the sun? Because these storms that come from the sun have an effect on the things in our planet. So it of course causes aurora, which are beautiful and everybody wants to see them. But if it is a strong storm, then it can affect the communication satellites, satellites in space, communication on the ground, power grids on the ground, and then GPS satellites, everyday activities related to that, aviation, and then human space exploration, because they have the same kind of effect that cosmic rays have on the genetics and human body and things like that. Okay, so what happens when they come to Earth? So coronal mass ejections are these big blobs of plasma that are embedded in magnetic field, right? So when they come to Earth, they compress the Earth's magnetic field, and they cause oscillations in the Earth's magnetic field, which induces current on the ground. So changing magnetic fields induces current, right? So it induces current on the ground, and then oil pipelines, power lines. So they have a corrosive effect on the oil pipelines, and then the power lines can melt and then overload the power station and things like that. So that's what happened in the Quebec blackout during the 1989 storm. In March 13, 1989, and this figure shows this is the regular auroral zone, which ends a little bit above the northern, the US-Canada border. And then the auroral zone then was up until here. So people in Cuba also saw these aurora. And yeah, it overloaded a power station in Quebec and shut it down for almost 12 hours. People did not have power for almost 12 hours in Quebec and in New York, New Jersey, and places there. Okay, so solar flares, basically, they send out these radiation storms, right? They have an effect. They heat the upper atmosphere of the Earth, which means that they can expand the upper atmosphere, and it has an effect on the low Earth satellites. So it causes drag on the low Earth satellites, and basically it's unexpected, so you can't correct the orbits, and it can crash on the ground. So that's what happened to Skylab. Ironically, it was observing the sun and doing space weather observations, but it was an unexpected drag and ultimately crashed on Earth. And then these flares can also cause ionospheric disturbances, which causes radio communication blackouts. So what can we do to avoid them? So obviously we cannot avoid the storms, solar storms, but what we can do is we can monitor the sun, monitor these storms, and try to mitigate the effects that it causes. So how I'm doing that is using some of the diagnostics as to do the predictions. Firstly, to do the prediction for geoeffectiveness, whether it will how much effect it will have on the Earth, and whether it will have an effect or not, that kind of thing, and to predict when a solar flare happens itself. So for predicting geoeffectiveness, I'm using these features on the sun called chromospheric filaments and coronal sigmoids. They will act as diagnostic for getting the geoeffectiveness. So basically they give out CMEs and flares, and that can be used for geoeffectiveness. And then acoustic waves, which are inside the sun, we plan to use them for predicting solar flares. And all of these are connected. In the end, you will see that it all comes together because CMEs and flares can give rise to each other, or they can occur independently. And so each of these methods can be used for predicting either of the cases. Okay, so firstly, we want to establish the relation between filament and ICMEs. So ICMEs are these interplanetary coronal mass ejections. So basically, they are CMEs that start from the sun, and then when they are in the interplanetary space near Earth, they are called ICMEs. So we want to see if when the filament erupts, it retains its actual orientation as it traverses in the interplanetary space. Okay, so how we are able to do that? And so let's start with the filament definition. What is a solar filament is basically these kinds of condensation of cold plasma suspended in the hot corona. So cold is like 10,000 Kelvin, and so that corresponds to like chromospheric temperatures. So it's chromospheric material sitting in the hot corona. So how are they able to do that? Basically there is this twisted magnetic field lines called flux ropes, and they rise up to the heights of corona, and they can, they hold these prominences in them. So there's twisted magnetic field lines, and the prominence kind of sits inside them. So that's how they are able to be in the corona. And then, so prominences are basically filaments when seen on the limb of the sun. So it's called prominences. Filaments have these properties or directionality, which are determined by looking at barbs. And barbs are these features that look like extensions coming from the spine of the filament. So this is the spine of the filament, and these are the barbs. So we want to use this directionality to determine the actual magnetic field of the filament to get to know when an eruption happens, what happens, like when it comes to Earth. So that the directionality is called chirality, and you see that there's the spine of the filament, and these are the barbs that is coming out of them, and they have this. They are either right directed or left directed, and using a magnetogram, which gives us magnetic polarity information, you can tell whether the actual field is going that way or opposite that way. So that is one method using barbs, but not all filaments show barbs. There are like less resolved filaments, and then the active region filaments are small. They don't have barbs, or they don't show barbs. So in those cases, we can use what are known as post-flare arcade loops, which are loops that form after a flare occurs, and so you can use the axis direction you can use the orientation of that to see to get the axis direction. And also there are fibrils, which are features adjacent to the filament. They also have this right-handed and left-handed directionality, so you can use that also to get the field direction there. So we are using magnetograms to get the field direction, and we have the filament here. So this is the filament, and then the magnetic field that shows negative here and positive here. I don't know if it is clear there, but so using the barbs and the magnetic the magnetograms, you get the direction of the actual filament, and what we take is only the vertical component of that actual field, so northward or southward. So for the data, I'm using H alpha data from from NSO GONG, which is the Global Oscillations Network Group, and Kanzil Solar Observatory. And for magnetograms, I'm using HMI and SDO, HMI, and MDI magnetograms. So what are CMEs? Oh, let me play this movie. So CMEs are, as I told, they are like these big magnetic clouds of plasma that are embedded in the magnetic field, right? So filament eruptions can lead to magnetic fields. So the one that you saw earlier was a prominence erupting, and you see that it'll erupt and then comes out as a big blob of plasma. So depending on what the cone angle of the CME is, whether it is like more than 120 degrees or less than 120 degrees, they are called halo CMEs or narrow CMEs. So narrow CMEs usually don't have much effect on the Earth's magnetosphere, but halo CMEs are the most probable ones that reconnect with the Earth's magnetosphere and cause geomagnetic storms. Okay. So here I show you an example of the halo CME. So it looks like a halo around the sun when it is coming towards us. So it is this one. And this is taken from this satellite called SOHO, which is sitting at the L1 Lagrangian point between the sun and the Earth line. And yeah, it is at a vantage point where it can observe the sun continuously and monitor these CMEs. So what is happening here is that the CME occurred and all the particles that are coming from the sun basically hit the satellite and caused static on the CCDs. So once the CME erupts, this is the structure that it has in the interplanetary field. So this is the flux rope that I was talking about before, and the filament sits somewhere here. The filament is a very small portion of the whole CME structure, and we want to get the axis direction of that flux rope to see if it will reconnect with the Earth's magnetic field or not. So basically, if it is southward pointing, then it will definitely reconnect with the Earth's field, because the Earth's magnetic field is northward. It goes from south to north, right? And if the CME has a southward pointing field, it will connect with the Earth's magnetic field at the nose of the magnetosphere and cause geomagnetic storms. Okay, so for the halo CME's data, I'm using the list of CMEs given by the CDAW website. It gives me the date and time of when it occurred and the speed of the CME, the acceleration, so using which I can get to know when it will arrive at Earth, and then if it is a halo CME or not, like the cone angle, and the source of where it erupted from and whether there was a flare or not with it. So using that, I go back to the sun, look at that location, and see if there was actually a CME occurred from there or not, and then get the axis direction of the active region or the filament using the methods that I showed you before, using the chirality, and then come back to Earth and then use the parameters that I get from the satellite called Advanced Composition Explorer. It is also at the L1 Lagrangian point between the sun and the Earth, and this gives me all these magnetic field, plasma temperature, proton density, flow speed, pressure, and everything, all the plasma parameters at Earth. Along with that, I use the DST index, which is a measure of the change in the magnetic field, and they are taken from Earth-based magnetometers. So I use all the parameters and plot it in this way. So on the x-axis, I have time. And usually between fastest and slowest CMEs, it takes between 1 and 6 days to arrive at Earth. So that's why I have about 6 days here. And I want to know if it has an ICME structure or not first. So this is the solar wind, and we have the ICME structure. So firstly, I look at the total magnetic field, which is shown here, to see if there is some variation or not. If there is some variation, then I go back to see flow speed, proton density, flow pressure, etc., where you see this CME structure, because when there is a CME in the solar wind plasma, there is this shock. And then as the CME goes through the satellite, there is a decline in the proton density and flow speed and such things. So you get to see that here. And what we want is the BZ direction. So look at the positive, like if it is positive, then it's northward, and if it is negative, it's southward. So I see the BZ to see if it is, like, it will have a geoeffective, it will be geoeffective or not. So I looked at all the CMEs between 2007 and 2017, and there were like 30,000 CMEs. Fortunately, there were only 83 CMEs, halo CMEs, that were bound to Earth. So then I was able to configure them between, I was able to classify them between northward and southward, about 71 of them. And then the rest, about 12 of them were like unclassified because it did not have a ICME structure, or it had like a different kind of structure, like a CIR or something like that. So this is my result. You can see that most of the time, if it was northward on the sun, it was northward at Earth, then southward at Earth, and southward on the sun. But sometimes it was different. It had an opposite configuration. So we think that maybe there was an obstacle, and when the CME erupted, it encountered this obstacle and rotated, or somewhere in the interplanetary space. So this was the first time ever somebody has used chirality of filaments to do space weather predictions. And we see that 84% of the times the magnetic field orientation is retained after an eruption. And so we want to do geoeffectiveness prediction. So you see that half the number of times when it is northward, you don't have to take a measure, because usually northward CMEs don't have any effect. So you don't have to shut down the satellites, or take care of the power grid or anything like that. So minimize the losses. And another important result is that because filaments are observables and chirality is an observable, you can automate chirality detection to do space weather monitoring. So that's what we want to do next. We want to do train some machine learning models to classify between right and left chirality of filaments. So I haven't started doing this yet, but hopefully in the near future I will start. But I have the training data set available with about 100 in each case from the Gong H-alpha data. And then I'll be getting some more from Helio Research, which has a lot of filament observations, and they are high resolution. Okay, so far, I don't want to show you that. So far, we've looked at chirality observations, which are observables, and then we're only taking the northward or southward component of that. So what we want to do is get the actual orientation of the filament. So for that, I'm using vector magnetograms from the HMI and MDI. So they give the BR, B theta, B5, which are the components of the magnetic field. And using that, I want to also compare with my chirality observations, if I did a good job or not, and if the vector magnetograms are giving me the same directionality as what I got from the chirality observations. And so initially what we wanted to do, that is at the sun. So at Earth, we want to do flux rope fitting using the same BX, BY, BZ of the flux rope at Earth. To get the actual orientation of the actual field there. So that's what we want to do first, but these people published almost like from 1995 until now, all the flux rope fitting data from all the ICME flux rope fitting data. So now we will probably merge both our data sets and see if what I observed they show the same kind of actual direction or not in their fittings. So this gives us a strength and the actual angle of the orientation of the axis of the flux rope. So this we will know, using that we will know where the interaction will occur and how much effect it will cause and things like that, okay? So I've done the vector magnetogram work for one of them. If you can see these small arrow marks, they are all pointed towards that direction. And the filament corresponding to this, the chirality also gave me the same result, like it was northward oriented. So this is the corresponding H-alpha active region in the H-alpha, and this is the corresponding magnetogram. So next what I want to talk about is the sigmoid and filament relation. This is the work that I did during my second semester here in GSU. And we want to look at sigmoids to do similar kind of space weather prediction. So basically sigmoids are these S-shaped or inverse S-shaped regions on the sun, and they are usually visible in X-ray, which means that corona. So these are at coronal heights, and filaments are at chromospheric heights. Filaments are like chromosphere, and then there is this X-ray sigmoids we see in the X-ray heights. So, but in the filaments can be sitting inside these sigmoids. So what we want to do is we want to see if this S-shaped or inverse S-shaped have the kind of correlation with the, the right-handedness and left-handedness of the filament. Because that, if that is the case, then we can just use these S or inverse S-shaped things on the sun to see if it causes a CME, it will be a geoeffect or not, because these are big things and you don't have to have high resolution images. They are easily seen. And they are also highly active regions. They give out a lot of CMEs and a lot of flares. So that is why it is important to study sigmoids, and also to understand how these form and things like that. So basically, theoretical models predict that there is a correlation between the S-shape and inverse S-shaped of the filaments to the right-handedness and left-handedness. So it's all both one kind in the models. But what we observe is the opposite. So either kind of filament can be inside either kind of the shape of the sigmoid. So that has implications for the modeling community, which model like both of them as the same kind. So next, what we want to see is the helicity of in both these regions, in filaments and in sigmoids, to see if when we get the helicity calculations, it shows a similar kind of results or not. So they have done helicity observations for, people have done helicity calculations in active regions, like if there is an emerging active region, helicity on that, and the already existing ones. So both show an opposite correlation. So they both have opposite sign of helicity, which means that they can, it can cause reconnection, and then a flare can occur from those regions. So that's what we want to do for this also. So next, I want to talk about the method that I want to use for studying active region filaments and doing space weather effects using that. So, okay, basically, active region filaments are small and they have very unresolved barbs. So that means that we have to use something that is like a big telescope to resolve these barbs, right? So that's what DKIST will do. It's an upcoming big telescope. It's 4-meter monolithic Gregorian. It's situated on top of Haleakala in Maui, and this is the big telescope. And it will do full Stokes polarimetry in a wide range of wavelengths, starting from the visible well into the infrared. And it gives very high resolution, like 0.03 with AO and 0.15 without AO. Okay, so earlier this year, I had applied for this matching funds program that Pete talked about earlier. So to use this DKIST data to study active region filaments to do space weather predictions. And also to study filament formation, evolution, and things like that, like how mass motion occurs, where the barb foot points and the filament endpoints, where the endpoints lie, like whether they lie in the chromosphere or in the photosphere and things like that. So that has like implications for filament formation and such things. So that's what we want to do for this. And DKIST provides a suite of instruments to be able to conduct the study. It has a bunch of instruments that, two of them are imagers, and all of the other instruments are spectropolarimeters. So that means that it will give magnetic field and strong magnetic fields. So now I want to use some of the instruments to do the science that I told you about in the previous slides. So now, this instrument we want to get from WISP, we want to get iron 1 and H alpha, which will show us magnetic features in the photosphere and H alpha features in the chromosphere. And finally, DL NURSP for getting using 10830 nanometer helium 1 line to get the chromospheric magnetic fields. All right. So magnetism is the main thing that affects the polarization in the light coming from the sun, right? So there is Zeeman effect and there is Hanley effect. So Zeeman effect is it's in the strong field regime where like the magnetic field is about 100 to 3000 Gauss, and it basically splits the line, is like one single spectral line into multiple lines where the levels are split into multiple levels and the transition occurs between each of them. And whether you're looking at it from along the field line or perpendicular to the field line, you see circular polarization, which gives such profiles, and then linear polarization, which gives such profiles. And in Hanley effect, what happens is it's basically scattering polarization. So you have your light at 90 degrees that is like polarized. Without a magnetic field, it's just polarized. And then what magnetic field does is it rotates the polarization. And in the direction where you see, it rotates in the opposite, or the clockwise or anti-clockwise. And then in forward scattering, what happens is you're looking directly into the surface of the sun, and if there's no magnetic field, you don't see any scattering. You don't see any polarization, but if there is a magnetic field, you see the polarization. So what effect it has is basically like if you're looking at 90 degrees from like near the limb of the sun, you see full polarization when there's no magnetic field, and the intensity reduces as you add magnetic field into it. So these are Q, which is a Stokes Q polarization, which is the linear polarization, right? And in the scattering polarization, where you see it like directly into the surface of the sun, you have nothing when there is no magnetic field, and the intensity increases as you start adding magnetic field with the strength. Okay, so now what these instruments collect is the IQUV polarization vectors, and what sun gives is the polarization of light. But what we want to get is the magnetic field, temperature, and such physical things that are on the sun that are affecting affecting the light, right? So I want to use this code called Hazel. It is an inversion code. It's a Hanley and Zeeman light. It basically solves radiative transfer equations considering all these, physics of formation of lines, and starting with like a model photosphere or chromosphere. And this is the fitting that so I'm trying to run this and learn how this works, and then to interpret the information that it gives and things like that. So this is a fitting of 1 pixel. So it's in 10A30 line. This is the I, Q, U, and V. And the blue basically shows the signal, and green and orange are fittings during the different runs. So I'm using a supercomputer to run these things. So it can run in like serial and parallel mode. So I can run it on my computer and on the supercomputer as well. So, okay, next we want to talk about the solar flare predictions using acoustic waves. So these acoustic waves are generated inside the sun. So how they are generated is basically these hot plasma that is coming up from below. They cool down when they reach the photosphere and then go back down, right? So when they go back down, they travel at supersonic speeds, and that means that they can give these vibrations in like different frequencies and different all directions. So that's what you see here, and these like small frequency waves can get refracted when they go into the sun because of temperature gradient, and they get reflected at the photosphere. And higher frequency ones take longer paths, and then they can get out of the sun. So why these smaller frequency one gets reflected there is because when they reach the photosphere, there is a lot of density stratification, and that induces this what is known as this acoustic cutoff frequency. It's just like in a potential barrier where you have, so here you have the sun, the photosphere, and then all the small frequencies which are less than the acoustic cutoff frequency, they get reflected and they form ultimately they form like a 3D standing wave inside the sun. And then all these waves above the acoustic cutoff frequency can escape into the atmosphere. So if you're observing in different heights in the atmosphere, we'll probably be able to catch these waves. But what we want to do is use the low frequency ones to see if we can see them before a solar flare occurs. So, but why is that? Because most all of them are like going away, not coming into the atmosphere, coming into the atmosphere, right? But the thing with acoustic cutoff frequency is this is the cutoff frequency in a non-magnetic atmosphere. But if there is a magnetic field, it reduces the cutoff frequency. So it has this relation. This is with the magnetic field, and this is the acoustic cutoff frequency. And theta is basically the magnetic field angle that the magnetic field makes with the local normal. So it reduces the cutoff frequency in the local region where you have the magnetic fields. So this animation shows how this might be happening, like how it might be reducing the acoustic cutoff frequency, and then how these, so when the acoustic cutoff frequency is reduced, these low frequency waves can escape into the atmosphere. So this shows how it happens. Sorry. Okay, so this is the flare that happened in the post-flare arcade loops that I was talking about before. And it shows the animation of how, oh, wait, let me forward it a little bit. Okay. Okay, this is the flare. And you have the animation of what the magnetic field might be doing. So, yeah, so the idea is that the magnetic field comes together to reconnect and give out the flare. But when before the reconnection happens, they do this, right? So when they do that, they change the angle theta at the surface, and that's what changes the acoustic cutoff frequency and lets out these lower frequency waves into the atmosphere. So now we are observing lower frequency waves. We are able to observe now lower frequency waves in the atmosphere. So if we put these instruments and then catch the lower frequency waves, probably we'll be able to do solar flare predictions, right? So that's what this instrument does, magneto-optical filters at 2 heights, or MOTH. The data that I have from this instrument was taken by Stuart and his team during the South Pole summer of 2003 in December and January. And then, so it takes measurements at 2 heights, potassium and sodium, which have a formation height of like 420 and 780 kilometers above the photosphere. It observes in left and right wing of each of the lines. So we make Dopplergrams out of them and do the analysis. So because we are observing at 2 heights, we want to get the phase difference between those 2 heights of the waves. So we want to do cross correlation between them and then get the phase difference and make travel time maps. So travel time is proportional to the travel time of these waves that are coming from the potassium to the sodium layer are proportional to the phase difference, right? So we make these phase travel time maps of the region where we want to do the analysis, and then we make moving travel time windows of like 3-hour averages to get good signal to noise ratio, and like step it by like 5 minutes and 12 minutes to see if we see these signatures before the flare or not. So this is an example of potassium. Oh, that's not Wikipedia. This is this MOTH. Okay. So this is an example of potassium Dopplergram, and this is sodium Dopplergram, and this is the region that I'm going to show you next. So there's a filament here that erupts and becomes a CME, and then you'll see a flare that is happening here. And this is the travel time map at 4 millihertz, which is below the cutoff frequency, acoustic cutoff frequency. And these two happen at different, like the frame rates of these are different, so you have to watch both of them separately. And in the end of this, you'll see that all of these features here become blue. So T is the time when the flare happened, and when it's becoming blue, that means that all these waves the 4 millihertz waves are traveling in the atmosphere. Until then, they were like trapped inside the sun, right? So you see that if they're trapped, it's like it has 0 travel time, and then if it is, so it's becoming blue, that means that it is traveling in the atmosphere. So we are able to see these waves. And that's what happens in another flare. So this is the region where the flare occurs. It occurs twice as it goes through. And, oh, sorry. Okay, and so this region corresponds to this region, and this region corresponds to this region. And this region, like it's very magnetically active. That's why it shows all these blue travel times. But the flare occurs here, and if you see carefully, you will see that before the flare occurs, this becomes traveling during those times. So T1 and T2 are the flare times, like when the flare occurs. Okay, I'll let you watch it for some time. So, and after the flare occurs, it becomes green again, which means that it gets trapped again. Yes. So use it for. So I have 3 flares, and I make these boxes inside this big box. That is just to show you where to see. But I take wherever this blue occurs, I put boxes and then take averages of the acoustic wave signatures, and that's what I plot here. So let me play this movie also. So this is a 6 millihertz travel time map, and this is a 4 millihertz travel time map, and this is what you saw in the previous slide. So here I have intensity of the flare in EIT. That was the dark green movie that you saw before. It's extreme ultraviolet light. And blue and green are acoustic wave signatures in 4 and 6 millihertz. So you see that. Okay, and these are when the flares occur, the first flare that I showed you and the second and third flares. So you see that start seeing the flare signature in acoustic waves about 2.5 hours for the January 7th flare. And you see this variation in 4 millihertz and 6 millihertz. So 6 millihertz are supposed to be traveling because they are above the acoustic cutoff frequency, and 4 millihertz are supposed to be trapped. So during the flare, what is happening is we see this 4 millihertz becoming traveling waves, and 6 millihertz, their travel time is dropping. So that's what we see in this flare, and also here for the second flare. So the second flare happens here, and we see the signatures here, and also for the also for this one, we see the same behavior in 4 and 6 millihertz signatures. So for 4 millihertz, it's kind of the theta that is changing and then opening the door to let off these low frequency waves into the atmosphere. But for the 6 millihertz, I think that so the magnetic field changes the temperature and the density and things like that in that region, which has an effect on the sound speed, changes the sound speed. So if the sound speed changes, then the travel time of these waves, it affects that. So, and somehow it is affecting that. It is not completely clear what might be happening for the 6 millihertz. So we have to investigate that more. Okay, so I think that's all I want to talk about that. And so this is just a summary of what we see and what we see, how many flares we see, and how many hours before we are seeing that. So the January 8th, the second flare on the January 8th, we say that it's like 9 hours before, but it's very like a very active region, and it's like showing a lot of activity, and that is when one of the flares had already happened. Maybe that is the reason we are looking at it like 9 hours before. And so this is also a travel time map of one of the flares that Stewart and his team had looked at before, which is not the 3 flares that I showed you. So it shows this similar kind of like brightening here that they observe about 2 hours before the flare occurred. So this was kind of the motivation of like doing this work to study the acoustic wave behavior before the flare occurs. So apart from this flare, we have looked at 3 other flares, and now we want to do similar analysis for other more flares, so that we know that this is the kind of behavior. It's a trend and not a just a fluke or something. So, and also we want to analyze in quiet regions during the flare, so that we're not seeing something that is only happening it's not happening in the quiet regions. And then if we want to do analysis for smaller travel time windows to see exactly when we start looking at it. So the moth data allows me to do that, to do analysis on different flares, more number of flares, because the data is available during these time windows when there were like a lot of flares happening. So this is a light curve from X-ray light curve from the GOES satellite, which observes the Earth and the Sun. And it shows what is the intensity of the flare, like an M-class flare or C-class, or what kind of flare it was. So the flares that I showed you was this one, and the one that happened here, and also this one. So I have to still do the analysis for other flares in the data set. So currently, the methods in use for doing the predictions are for CMEs. There are nothing, and for studying geomagnetic storms, like there are some models available that predict the SEPs like about 1 hour before they arrive. And there are other flare prediction efforts that are in place, like machine learning at the astroinformatics group between astronomy and computer science at GSU. They are looking at the magnetogram data for studying flares, like when it will happen, when it might happen, or to do the predictions. Sorry. And I talked about, I showed you how we can do space weather effect predictions using some of the diagnostics that we have, and solar flare predictions using acoustic waves. It has wide implications in to do CME predictions as well, because flares and CMEs can occur together or independently of each other. So if we can do flare prediction, we should be also able to do CME predictions. And then further, small field of view telescopes like DKIST do not know when to point to a flaring region, because they don't know when the flare is going to occur. So for those cases, if we are able to see acoustic waves before flare occurs, we will have enough time to slew the telescope to that region and observe the initial phases. Because most of these small FOV telescopes, they don't start observing the flare during the initial phases, and they miss out on that. So, and it also has implications for UV variability studies. So, okay, this is my timeline. I've done some analysis so far, and I'm doing the flare analysis now. So I'll be continuing to do that in the early next year and do a DKIST proposal to do the observations. And so most of the work that I showed you will be done in probably the next year. And probably in 2 years, I'll be here again talking to you guys about these work. And then this is probably imaginary, but I put it anyway there. So, all right, I just want to thank everybody, my advisors, Pete and Stuart, for all the help and advice, and also for tolerating me, and Manolis and Rafal and Valentine for being on my committee. And so the department and Dr. Pratt for the supercomputer, and all the satellites and ground-based observatories for the data, and the mod data with Stuart and his team at South Pole. And the DKIST for the matching funds program, and NASA Finance that is paying my salary these days, and all of you for being here. Thank you. And this is my summary slide. If you want to ask me questions, you can ask me now. So my cat was being very nice and listening to my talk, so I put a picture. Yeah, he's here.
Does he have any questions?
So Valentine, do you have any questions?
Yes, can you hear me?
Yeah, I can hear you.
So, Aparna, this is all very impressive. You are in the flare part that kind of indicates that we might be able to say something about when flares are going to produce. If you have observed the filaments, you can also tell us what the orientation is going to be. So all of this is really the holy grail of space weather. So it is really totally impressive how much you are trying to achieve, and I'm very excited. So yeah, congratulations to you, to the Georgia State. It's a totally impressive study. I would like to have you here at NSO making this same presentation, because it does have a lot of implications for many of the things we do here at NSO. So that's what I want say first, and then I have specific questions. Let me start with with the last part, with this multi-height heliosseismology. You're using moth data. Is there any other data set that you can use for having better statistics, more flares? Can you use HMI and AIA to do multi-heights with the AIA would be in intensity, not velocities, but then HMI velocity, and AIA observes the chromosphere. Is there something like this that you can do? I mean, MOTH is great, but you probably need better statistics.
Yeah, I think it works better with mod because it is looking at lower heights, and these energies are, I mean, the wave energy is still there, and they are not mode converted or anything. So, looking at coronal heights using HMI, AIA and all that, I think they might they might not show as much signal. But I think some people have done these studies using AIA. So yeah, maybe we can put all of everything together and
or
study.
Perhaps, so MOTH is observing only from the South Pole, correct?
Yeah, I think so. As of now, yeah.
It would be ideal to have a place to put it and do more regular observations. I think it's very impressive what you are finding there too. And now let me go to the first part of your talk. I think you said that
So, can I interrupt you a little bit? So, Valentine said he can be here like about 10-15 minutes after the talk, after the audience questions. So, should we have audience questions first and then?
Okay.
So, Valentine, can we have audience questions first and then?
Yeah, thanks for that. Sorry that I have to.
No,
run.
It's okay.
Yes. So my question, I think you
Oh,
said
okay.
that,
He has to run. Fine. It's okay.
in the first part of your talk,
Yeah.
you said that in 84% of the cases, when you infer the orientation of the north-south direction of the filament axis using the barbs and the chirality rules, in 84% it does agree with what is observed in the interplanetary magnetic field. I mean, I think that's absolutely an outstanding result. I mean, it's absolutely great. There is nothing that can really looking forward to the paper that is in review right now. But then, I think this is great. Now, you said then later that the helicity of the sigmoids and that the helicity of the filaments don't agree that well. Is that correct?
So I haven't looked at the helicity, but I've only looked at the features of the. I've only looked at the features like sigmoid, the S-shape or inverse S-shape, and the chirality of the filament inside them. So that doesn't agree. I still have to look at the helicity. That's an idea that I have. I don't know if it'll work or not, but
Okay.
yeah.
But then so can you go back to what you were observing these sigmoids? So
Can you see? Oh, which one?
So next one, I think.
Oh, okay.
Well, it's actually not that important. So the bottom line, my question to you is, if the helicity of the filaments is so good as to tell us what the direction of the CME of the magnetic field is when it approaches the Earth, we probably don't need to look at the sigmoids. Maybe the sigmoids are less relevant, and we just need to make better measurements of the helicity of the filaments, either through barbs or through the spectropolarimetric observations that you also explained. Is that correct?
Yeah, maybe. I don't know. I have to look at it.
Yeah, I mean, I like better the helicity of the magnetic field than the signal. So I'm very happy to see the result.
I see. Okay, sure. I'll keep that in mind.
Yeah, that's all questions I have. I think it's very impressive work.
Okay, thank you.
You are going to solve all the problems we have with the space weather.
Do we continue with questions here now?
Yeah.
Here comes second.
Okay. Thank you, Valentine.
Very impressive work, Aparna. I have two questions also, one with the acoustic So if I understood well, you're using sunquakes to predict hours in advance of a flare happening. And that flare might lead into CME. What is, that is so impressive, I think, and I wanted to know if this is in context, how in advance are other predictions and other groups with other observations have come, because you're talking about hours.
Yeah. Yeah, so like they are able to do SEB predictions from some models for about that's about 1 hour. They give 1 hour ahead time. But other than that, Soho is looking for the CMEs, and so it's about like 8 minutes warning for the no, about half an hour warning for the SCPs from using that, because if there is an eruption and we want to be ready for the SCPs, that will give us like half an hour time, and then for the CMEs about few days after it sees that there was an eruption. So it gives about so much time to be prepared for, but it doesn't say whether it will be geo-effective or not. And so that is the main thing about the study, because it can tell you whether there will be an effect or not. Because if it is a northward, then you don't have to take care of the things on Earth or in space, or at least the satellites which are inside the magnetosphere.
And the other question is that before, when you talk about the filaments, the sigmoids, you said that my question is which one is better to predict, and you said that, and actually
the helicity.
Yeah, he said that something similar too. But also you said that the sigmoids are easier to observe?
Yeah, when they form, they're like easy, because they're like big structures. You can easily see the shape. And they usually form in like there are like multiple spots, and because of the differential rotation and Coriolis force and everything, they form like on the sun. And there are these satellites observing in X-ray continuously. So yeah, it is easy to observe. So if there is a correlation, you don't have to look at the filaments, which are small, and sometimes they are not resolvable, and such problems.
But both are good predictors in your opinion, or one is better than the other?
So I don't think I can say like one is better than the other, but if we have like multiple modalities, multiple ways of doing the effectiveness prediction or something, it is better. So that's why looking at different things.
I was absolutely convinced it would be a one-to-one relationship between signals and it does say that.
Yeah.
So, really basic question, just because I'm having trouble imagining how it works. Could you go back to the slide when you're talking about the northward versus southward reconnecting with the Earth field thing?
Yeah, this one.
Yeah. So, wait a minute. Which way is the Earth pointing?
So the Earth is pointing upward. It goes from south to north, upward field.
Okay, and then the incoming stuff from the sun, is it pointing like this?
So if it points like that, it can reconnect there. If it is pointing upward, then it won't.
So if it's like this, we don't worry.
Yeah.
If it's like this, we
Yeah.
worry. Cool. Okay.
Any other questions? Okay, cool.
Thank you very much.
Okay, thanks.